Hi, I'm back in the shed. In this video, I'm going to talk about how we got to this point. This is the spindle for the lathe. I'm going to talk about the design choices that I made and the way that I basically mocked up what I was going to be doing with it. So to start with design choices, the goal is to take something like this. Now this is a red gum burl. It probably weighs about 40 kilos, I think. 35, 40 kilos, and it is, as you can see, it is not perfectly balanced, perfectly symmetrical. And to mount that up on a chuck like this, this is a Vicmark 120 chuck, 4-jaw chuck. The chuck's jaws are concentric, so when you wind, the whole lot comes out together, okay? And they have little dovetails in here that grip the work. So the goal is to be able to turn something like this, to quote my friend Tim, without killing myself. So that's why I'm building this lathe and abandoning the one that's sitting over there in the corner. In order to turn something like this, you need to be able to turn it very slowly to start with, and it's fairly big. I have a rule here somewhere. Where'd that go? There it is. So there you go, it's 530 millimeters across. So you need to be able to at least throw that much. I have bigger olive stumps that I have access to. So this thing is going to be able to throw up to 900 millimeters. That means that we want speeds not much north of 10 RPM, at least to start out, and a very heavy machine that's unlikely to be affected by the unbalance. So I've started out with the motor. Over the years I've gathered for myself large and overpowered machines because I've spent a lot of my life using very underpowered machines and scaring the shit out of myself. So that's why I've got the Bridgeport. It weighs 1.2 tonne. At no point have I ever gone, this thing is too light. It has been a borderline too small a couple of times, believe it or not, but too light. So I've gone with a 3-phase motor because I can speed control it with my VFD, and I've gone for 3 horsepower or 2.2 kilowatts. Now, in order to get a low speed, there are a couple of things you can do. You can get a lower speed motor, which I'll talk about in a second. You can adjust your speed with pulleys, which I'll talk about later, and you can control with the speed controller. So let's start by talking about how the motor is going to work. So a 3-phase motor generally comes in a number of poles. Spiders in Australia. Black hairy spiders, scary. Okay. 3-phase motors come in a number of poles. Most commonly, they will come in a 2-pole. So what that means is that for every cycle of your incoming electricity, the motor will go through 1 revolution. The poles will completely reverse and then come back to normal. So at 50 hertz, which is the common frequency in Australia, times that by 50 cycles per second, multiplied by 60 will give you the number of revolutions. That's about 3,000. You get some slip, don't understand that. There are people on the internet much smarter than me that can explain that if you really have to know that. But what that means is you end up with a motor that'll run at about 2880. 2800, 2880, depending on which you read. The next step down is a 4-pole. So for every cycle, you get half a revolution, and that'll give you about 1440. The next one beyond that is a 6-pole. So for every revolution, you get a third of a turn, and that gives you about 900 RPM. Finally, you get to, not finally because it's 12-pole, this motor is an 8-pole. So an 8-pole will give you a quarter of a turn per revolution, which works out to 750 RPM at 50 hertz. The trade-off is that you end up with 8 individual windings, lots of copper, very expensive. As you can see, quite massive. When I picked this up, I wondered whether I may have overdone it. But it's 2 horsepower, so it should be, oh, sorry, 3 horsepower, 2.2 kilowatts. It should be okay. So that's how we've come to this motor. I was going to go with a 6-pole because they are a fraction of the price, partly because they're a lot more common. When I rang up Gawler Motor Rewinders, they had ordered 5 of these, but they only had buyers for 2. So they offered me one at a very good price, less than a third of what the going price is. So normally these would be $1,600. Okay, so the next obvious way of adjusting speed is to use pulleys. I've spoken to Statewide Bearings, had quite a lot of back and forth with them, and they looked at my needs and came to the conclusion that I needed to buy these 10 groove poly V belts, pulleys, with a 9V belt. They were expensive. This lot here was $1,200. So what that will give us is a coupler. The shaft output is 28 millimeters, which for some reason is a weird, uncommon size for bearings. So the coupler allows me to go from 28 millimeters to 30 millimeters. 30 millimeters is as common as muck. And then I've got a pair of pillow blocks, and the taper locks for these are all in 30 millimeter. Likewise, the spindle is also 30 millimeters. So I've managed to keep them all the same size there. Makes purchasing all of this stuff a lot easier. I've also had to buy a couple of pieces of, I don't know if you should be able to see them there, a couple of pieces of 32mm plate that I got cut by Ferrocut down at Paraka. They are 32 at the right height and the right width to be welded inside the headstock when the time comes. They'll need a quick face-off to clean up the top, and they'll need some threads cut into them to take the bolts. Okay, so the last way of controlling the speed is using a variable frequency drive. These 3-phase motors will run out to 60 hertz. So normally incoming frequency in Australia is 50. These will run out, well, I run well beyond 60 hertz, but the power curve rolls off quite dramatically beyond 60. So 60 is as fast as we're going to run this thing. That's not a problem, that's fairly straightforward. But when you slow the motor down, you run into potentially problems, particularly if you want to go very slow. And I'm looking at going as low as a couple of hertz, maybe. So what last thing I want to do is damage the motor. The reason you would damage the motor is on the back end of the shaft, normally you would have a fan. So the speed of the fan, the speed of the motor dictates the speed of the fan. The slower you are on the motor, the slower the fan runs, but it's still consuming the same amount of power. So you can end up burning the motor out. To get around that, I have purchased this, which is an external fan unit, and that is single phase, so I've just picked up single phase off of that into my variable frequency drive, where my power comes in from my variable frequency drive. The other thing that I'm going to do is I'm going to control the on-off and the speed with a separate box. So I'm going to have to fabricate a little box to take these, which then either will have a magnet or a clip or some sort of attachment, probably a magnet, and I'll put that close to where I'm standing. What I don't like doing, and this is pretty much, so the headstock would be here. If your work is here and it's spinning, I don't like coming in here, turning the machine on, and then stepping past this rotating work to come in and work from here. So I'm going to bring that box around, it'll sit down here. There'll also be an e-stop mushroom on it. Probably won't be a true e-stop because that could potentially break things, but it'll be a stop that brings the motor, that'll actually use the motor to bring the spindle to a stop in a second or two. So I've got that wired up, and as you can see, I've got my 3-phase going in there. So that's all wired up, that's working. Not going to demonstrate that. The last part of that little puzzle will be that I really want to know how fast the spindle is going. So I'm going to use this tachometer, which, because it's not powered on, is blank. This tachometer, which has a little magnet and a sensor, which will go onto the spindle. I'll have to machine a little flat somewhere on the spindle, glue the magnet on, put the sensor in proximity, and then I'm also going to have to pick up 12 volt from somewhere. I've got a little 12 volt power supply sitting over there. That'll probably live inside the control box with this, and that will allow me to know exactly how fast my spindle is going. And that becomes relevant when you're turning, because you want to be turning at about a tool speed of about 40 miles an hour. I should have, so I think 65 kilometers an hour, and I don't know what that is in meters per second, but that's a lot. But you want it to be that speed, and you don't want it to be slower, it won't cut properly, you don't want it to be faster. It starts to become, well, it's dangerous, but also won't cut as well, and you burn your tool at workout. This red gum is incredibly hard, and it's also very dry. I have no idea when this was cut, but it's been sitting outside my shed now for 3 or 4 years. It's like concrete. That's one of the reasons that I will probably at the end of the lathe have a sharpening station, because I'm just going to be sharpening every minute or two, just due to the nature of the timber that I'm working that's available in Australia. So the final step was working out what the spindle was going to look like, how long it was going to be, and what features I wanted. I've got just a piece of bar stock that I machined up just to allow me to mock it up. So there's our main spindle. That's going to fit on there as a press fit. You can see it's quite polished and quite close tolerance. If I freeze this down and heat that up with a blowtorch, it'll slide straight on. I just haven't done it yet because once it's on, it's going to be really hard to get off. And then I will machine a journal into the headstock and also have a cap that goes over the top that holds the whole thing in place, and they'll be press fit or very, very tight. That's a tight slip fit. Obviously my 2 bearings and my tail bearing, end bearing, that's going to go onto the inside of the headstock. So you'll notice on these, can't see that one, but they both have a grease nipple. There's a grease nipple here. I won't be able to get inside the headstock easily and grease this, so I'm going to have to plumb that out to the back of the headstock so that I can grease it routinely. So that's yet another thing to do. So I need to machine a keyway into here for these two, a similarly keyway into this, and I need to machine in a flat, and I'm also going to put a spindle lock onto it. But because I've drilled that hole all the way through, I don't want to drill holes into this that will further weaken the spindle. So I'm going to put a keyway in here, put a collar around that, and then I'll drill a hole into the collar, and then I'll make a spindle lock. That allows me to get this off and actually hold the whole assembly still while I do that without damaging it. And as a final thing, I have bored all the way through, and on this end I just used a form tool to cut a Morse taper 1 into here. You can buy a spur chuck. This may not be big enough. I may take it off and put a Morse taper 2 in, I don't know. But you can buy a spur chuck, and that spur chuck, you can also buy them actually to go into the chuck, so I don't know which one I'm going to use yet. You can buy a spur chuck. That spur chuck allows you to just force the work up against it with a tailstock and hold it in place and turn the work. And then you would then turn your rebate onto here, that would allow you to hold the work independently. I figured I might as well do it now, so that's done, and that's actually a fairly large thread. So I've elected to use an M33 thread, and my lathe is not up to that. So I sent this off to Bealitz Engineering up in the Riverland, up at Wakery, and Neville has machined that into me. And I haven't got the collar handy, but that is a absolutely beautiful fit. So nice. So the last consideration is how long. I had a look at this here, and if you look at that, it's actually this shaft that determines how long everything needs to be. Because I need to allow for all these components. And in the end, I decided that I would run with 280 millimeters externally on the this is my headstock mock-up. I had a couple of goes at this. This is the second one. I did it at 250 square because that just seems a bit more uniform to me. Didn't work, too small, not enough space for this, just couldn't get this assembly in. So we ended up with 280 millimeters. Total length on this is 300 out to about here, and then we've got the thread on the end of it. I'm just going to put up a little bit of video of me producing the spindle. So here's that now. So this is the bar for the spindle. It's 400 mil of 4140, 50 mil in diameter. I'm going to turn it down to 30 mil for most of its length. First thing to do will be to get it centered up, and then we're going to bore it from one end to the other. So let's get started. That'll do.
Unfortunately, I don't have any more footage of making the spindle. My camera went flat, I ran out of SD card, and I reckon I lost some footage too. But what you're seeing here is me turning the main shaft down to the diameter. I've then turned the journals. It's turning a bit of a taper, this lathe. I don't think that's fixable. It's just a very cheap lathe. I then bored a hole from one end to the other, turned in the details for the thread and for the cover that's going to hold the whole assembly onto the headstock. And then I used a tool to turn in the Morse 1 taper. And this is what it looks like, all sprayed with lanolin, wrapped up in cling film and going off to the engineering place to have the thread cut.
So the spindle's finished. Hope you found that interesting. That's what I've been up to, amongst a whole bunch of other stuff. And I've got another video coming out soon, which will be fabricating the legs for the bed. No worries. Thanks for watching.